Thank you very much for the invitation to do this. In fact, for me, it is a real pleasure to be here back in summer, having been in autumn for about 2 weeks. Coming back to give a summer school is something that is very invigorating for me, coming from Glasgow. So Desh's challenge was to talk about the science, of course, but actually extend the lecture and include some information about basic principles and basic fundamentals. So I'm going to talk a bit about multi-scale modeling, and that's why I chose this topic, also because it's related to the topic of the conference, right? Devices of life and technology. And you can think of nanomaterials as a device of technology, but there's also some parallels to life, which I won't really get into, but this self-assembly from solution is really something that happens that is quite ubiquitous. So this is brief outline. So I'll start to about fundamental principles of molecular modeling. For those of you who have already done molecular modeling, this will probably be quite boring. So you can probably check your email for a while, but hopefully it will be useful for some of you. Then I'll talk a bit about coarse graining and this introduction to multi-scale modeling, how we can kind of bridge the time and length scales of our simulations to attack other problems that are more complex. And then I'll go into self-assembly and the principles of computational materials design. And then I'll start with the part of the science about the work that we've been doing now over probably about almost 20 years on this topic. So I'll go through pretty much 20 years of research in about half an hour, hopefully. And then at the end, I will give you some recent updates of a new kind of model that we've been developing that involves chemical reactions. Okay, so if you want to do modeling, and this is true about any model, it doesn't have to be molecular modeling, right? So you first have to get information about the system. So set your anchors. What do you know? What do you want to know, etc. And then you need to develop a model for the system. Okay, and then you need to solve the model. So you have a simulation method, right? So this is the first difference that is very important. Is the difference between a model and a method. Okay, this might seem trivial to you, but actually it's incredible how many students struggle to understand this. So the model is your representation of reality. So it's translation. As an engineer, I always tell this to my students. The main goal of an engineer is to translate reality into mathematical equations and then back. Okay, and so the model is our abstraction of reality into a set of simplified concepts that can be solved mathematically. Then the actual method is the way that we solve that mathematics, right? So this is true for molecular modeling, of course, but also for finite element modeling, any other kind of modeling. So I don't really have time to talk about the methods themselves, right? So this is this other step here. Just to say that there are two classes of methods used to solve molecular models, Monte Carlo and molecular dynamics. They are essentially the integrators that we use to solve the equations of statistical mechanics. The main difference between the two is that molecular dynamics is Newtonian, so follows a Newtonian trajectory, so calculating forces over time, whereas Monte Carlo is stochastic, so it's kind of based on random numbers, and they progress through two different paths, but the aim is to reach equilibrium, thermodynamic equilibrium at the end. Okay. If you want to know more about the methods, I'm more than happy to talk about them later. What I am going to talk about in more detail is the model development, right? So what we conventionally call a force field because it defines what forces happen in the system, okay? Right, so what is a force field? A force field describes all the interactions between all the molecules or atoms or sites in your system, okay? So we need to define our molecules or our atoms, and then they need to interact with each other, right? And those interactions determine, for example, in Monte Carlo, the way the probability of accepting or rejecting those random movements. And in molecular dynamics, they describe or they tell you how the system propagates in time over time. Okay. So in reality, of course, any interaction between two sites is a many-body problem. So you have interactions between two sites, then 3 sites, then 4 sites, etc. ad infinitum. In practice, however, anything beyond 3-body is pretty much negligible, and even 3-body interactions are quite often lumped together into 2-body interactions. And that's mostly to make the calculations tractable. There are 3-body models out there. They're quite rare, but they exist, okay? By and large, people use 2-body models to solve these equations. So we render everything into a pairwise effective interaction, okay? So then which interactions are you trying to represent? Okay, and here's a kind of non-exhaustive list of these interactions. So the first is repulsion. That's the shortest range. So when two atoms approach each other beyond this certain minimum distance, they repel. And that's just Pauli exclusion principle, right? The electrons don't want to be in the same place at the same time. So that's, of course, very short range. It only really takes place when the atoms are very close together. Okay. You also have electrostatic interactions, right? Between, you can argue that everything is electrostatic, and that is true. But what I mean by this is permanent electrostatics between permanently charged or dipolar or polar molecules. Okay, and this is a kind of really long-range interaction. We also have dispersion, right? So dispersion is also very well known, and this is happening due to induced dipole-dipole interactions. So when two molecules are polarizable, they approach each other, their electron clouds fluctuate, and they generate a mutually attractive interaction. It's always attractive between the two molecules. This is relatively short range, of course, not as repulsion, but longer range, but also still short range by computational standards. Then there's polarization. Polarization is much more complex, and in fact, my group has been doing some work on trying to represent these interactions in a very effective way, but I don't really have time to talk about that. So polarization happens when a permanent dipole or multipole induces a dipole in another molecule, and that causes, again, an attraction between the two. But this is an inherent multibody interaction, and so it tends to be lumped together into these pairwise effective interactions, okay? So there are, again, ways to explicitly handle polarization in simulations. That's not the topic of my talk. We can, again, explore this later if you want. And the final interaction is when you, oops, apologies, there we go. So the final one is this bonded interaction. This is essentially when you build a molecule based on atoms, okay? So you have to tether them together so that they behave like a molecule as they progress in time. So this is just an example of these bonded potentials. When you have two atoms bonded, let's say in N2 molecule, for example, then you would have a bond stretching potential. Typically, these are harmonic potentials of this form here, so it's a parabola. So anything, when the molecule is at the equilibrium distance, R0, then the interaction energy is 0. And then as you distort the molecule by extending or contracting, then you pay an energy penalty, okay? Same for angle bending. Okay, this is easy. And then torsion is a bit more complicated because different groups of 3 atoms or 4 atoms twist in different ways depending on their energy barriers. And so you normally have a more complex functional, which is described as typically a sum of cosines, okay? So there are other ways of representing this. This is the most common. That's the essentially approximation is in my talk, just show the more common ways of representing this, but there are other options, of course. So now non-bonded interactions take place between atoms that are in different molecules, okay? As I said, there are 2 types of interactions that are present in every molecule known, okay? And that's repulsion and dispersion. So it doesn't matter whether the molecule is polar or non-polar, large, small, etc. These interactions are always there, okay? And so we tend to lump them together into a very simplified functional form called the Lennard-Jones potential. Even if you haven't done simulations, you've heard of the Lennard-Jones potential. So this is it. This term here is the repulsion term. So R to the minus 12, very short range, and positive, okay? So the energy is positive in repulsion region. And then this second term is the dispersion energy, which is R to the minus 6, and it's attractive, right? So it's a negative energy. You put them together, you get a curve like this. Okay, so at very short range, beyond this kind of soft sphere radius sigma, the interaction is repulsive, the energy is positive. At longer distances, it is negative and attractive, but tends to 0 fairly quickly. And then there's a sweet spot, this well depth, which is defined by this parameter epsilon, which is where the molecules prefer to be. Okay, so if you have, say, a Lennard-Jones liquid, you can simulate it, and you'll see that on average, the molecules will reside close to this energy minimum here, okay? So the other small thing to say here is that because this decays very fast with distance, we normally truncate this at a cutoff radius called the RC, right? So cutoff radius. After that, there are many different ways, but essentially we render the interaction down to 0, okay? And there's ways to compensate that using long-range corrections, which again, I don't really have time to talk about, okay? There are, again, other options. This is the most common one. You can use more complicated functional forms like Buckingham or extended exponential, something like that, to represent the repulsive side. Or you can use even simpler models like hard sphere or square well. Okay, so hard sphere is just a repulsive hard sphere. Okay, and square well is something that represents this attraction using a kind of square well, as defined by the name. Okay, so they're simpler, computationally faster, but normally less realistic. Okay, so we have bonded potentials, we have Lennard-Jones interactions. That describes basically any molecule. But now if you have polar molecules, you have to add something to it, right? And that's at least permanent electrostatics. You may need to add polarization or not, but at least permanent electrostatics, you need to do it. So the equation to do that is the Coulomb law, okay? So you see the interaction decays as R to minus 1, so it's very long range. Remember, dispersion is decaying as R to minus 6, and we use a cutoff. With R to minus 1, you cannot use a cutoff, okay? So you use special techniques like Ewald sums and derivatives of those to account for the missing interactions beyond the size of the typical simulation box. Again, it is something that is mathematically quite involved, but conceptually, it is rather simple. So you approximate the missing interactions through a background charge, and you integrate that background charge using Fourier transforms, okay? So again, no time to go into the details of this, but just to let you know that there are techniques that are robust and well used to account for this kind of missing level of interactions. And this graph shows you just an example of the magnitude of these permanent electrostatics. So normally they're represented by assigning partial point charges on each atom, okay? So for example, in the water molecule, you'll see here, you would typically have a negative partial charge on the oxygen atom, and then 2 positive partial charges on the hydrogen. And of course, they need to balance out because the molecule has to be neutral. So those partial charges, they can be assigned in different ways, empirically or from quantum mechanics, etc. Again, this is something that my group has been doing some work on, but we don't have time to cover. But they are assigned in some way, and that gives rise to an interaction between those charges in the molecule. And this graph shows you the typical type of interactions between a water dimer forming a hydrogen bond, okay? So you will see that these interactions down here are the attractive ones, okay? So these are the OH, right? Interactions between opposite charges, one positive, one negative, they're all attractive. The pink one here is the one between the H and the O forming the hydrogen bond. So it is stronger than the others, of course, as you would expect. That is partially offset by the positive or repulsive interactions between the HH atoms and more prominently the OO atoms, right? When you put it all together and you add the black line, which is the Lennard-Jones interaction between the two oxygen atoms, you get the red curve, okay? So you'll see that this black curve is what you would get if you had a non-polar water model, right? And you see that, of course, as you expect, electrostatics completely dominates the interaction between water molecules, okay? You would expect that. I will tell you more about this balance between non-polar and polar interactions as we go along. But in this particular case, it is overwhelming, okay? And as I said, you can also include polarization interactions. Those are much more expensive to compute. And so you can use, essentially a choice is to use a polarizable versus non-polarizable model. And that's a very important modeling choice. But again, we don't have time to cover that. Okay, so that was in 10 minutes, more or less, a 101 of force field models. Now, in practice, what do you do? Okay, so the modeling part, I normally tell my students that the computational part of solving the problem is important, and sometimes we need to put in some effort into it. But actually, I think for me, the most important and useful part is the modeling. That's the creative part. Okay, that's when you try to again understand the physics of what's going on and translate that into a simple model that you can solve. Okay, as one of my postdoc advisors used to say, your model, and paraphrasing Einstein and others, right? your model should be as simple as possible, but not simpler. If it is simpler, you don't get the physics, right? If it's more complicated, then you're wasting time. At the very least, you're wasting time, and you're probably over-defining, over-parameterizing your model. So how do you choose the right model? Well, the question is, first, you need to understand your system. And so the right model depends on the system you're studying. And I will show you in the research that I'm going to talk about today, the self-assembly, the right model tends to have to be very simplified, because we're having to try to access very large time and length scales that you would not be able to access with atomistic models. So that's the first choice. How detailed should my model be? And here are 3 options to represent propane. Okay, this propane molecule, you have 11 sites, all the carbon atoms, all the hydrogen atoms in your system, and they interact with what is called an all-atom model, fully atomistic. You can simplify that. You can say, well, these hydrogens aren't really doing much there. They're very close to the carbon. This is non-polar. Let's get rid of them. And we coarse grain. That's what we call coarse graining. So we can represent it by 3 sites, which are not a carbon. They're a CH3 and CH2 group. Okay, so this is what is called the united atom approach. Okay, it's very popular, and we use it a lot as well, because in fact there's very little lost in going from this side to that side for a non-polar molecule. You can even go further and say, well, I don't really care about these 3 sites. They are close together. I want to represent this as a single site, make my computational at least 3 times faster, more normally, and I represent this by 1 site. Okay, this is kind of extreme coarse graining. I will show you the models we are using are actually of this type, right? So you represent 3 or more atoms as a single bead. So the answer is, which one is correct? There is no right answer. The right answer depends on the problem you're trying to solve. The same is true about electrostatics, right? So do we need to use charges, or is Lennard-Jones enough, right? And you might say, well, okay, depends on the polarity, of course, right? So for methane, you can say, well, you don't have to use charges, right? It's pretty much neutral. And with nitrogen, probably you can get away without, but it improves a little bit when you add charges. Carbon dioxide, I would say probably at this stage you do need to have charges because it's strongly quadrupolar. And then for water, it's obvious that you need to use charges, okay? As I showed you in the previous slide. However, do you really need to use charges, right? In the model that we are using for the self-assembly, actually water is this, okay? So yeah, do we lose information? Absolutely. Right? Is it real water? No, no way. Is it good enough? Yes. For the problem we're trying to solve. It is impossible to solve the problems we're trying to solve by using an atomistic model of water. No way. Okay? In fact, we saw a talk by Zoli yesterday where he wasn't even using water. It was an implicit model, right? So you implicitly describe the behavior of water through some fields in your simulation, and you get rid of it altogether. So again, it's a modeling choice, just like any other. And finally, you can also choose whether you use bonded potentials or not, right? So we tend to use a lot rigid potential models. They're much faster because we don't really care about the vibrations. But if you're simulating, for example, a spectroscopy profile or something like that, then you need to use flexibility. So again, it depends on the answer, the question you're trying to answer. So just a summary of this, let's say, flexible simple point charge model for water. Okay, we build this. So when we build a model, we make assumptions. And all of these assumptions are questionable. You can say, well, no, I prefer to do this or that, okay? So we first define that there are 3 atoms. Sure, okay, that's fine. But in fact, there are many models in which we introduce a 4th site or even a 5th site, okay? These are not real atoms, but they are important sites for representing the true electrostatic potential around the molecule, okay? Like TIP4P, for example, is a 4-site model. Water has 3 atoms, not 4, okay? But this is a better model because it represents the electrostatic potential better. But it's more expensive, okay? 4 sites instead of 3. So it's always a balance, right? This balance is always present, right? Do we need to introduce that complexity? If yes, we do. If not, we shouldn't. Okay, so 2 types of sites. The 2 hydrogen atoms are equivalent. You need to be able to flip the molecule symmetrically. Then this is the first big assumption, right? Include 1 Lennard-Jones site on the oxygen atom, okay? Not on the hydrogens. Okay, we could. There are models that include Lennard-Jones interactions on the hydrogens. And people have tried to argue that improves the description, okay? So it's an open question. Include 1 point charge on each atom, but total molecular charge is 0. Again, it doesn't have to be on the atoms. It can be displaced. You can have more than 3 or 4 charge sites. You connect the atoms by covalent bonds, right? But of course, there's only 1 type of bond, OH. Also 1 type of angle, HOH. And this is, again, another modeling choice, right? Many models, like the typical SPC model, is rigid, right? There is no flexible bonds or angles. You can choose to do it or not. So if you make these particular choices, that leaves you with a set of parameters, right? So in this case, the flexible SPC model has 7 free parameters. Epsilon and sigma for the oxygen, not hydrogen. The charge on the oxygen, because once you fix that, then you know what the charges on the hydrogens need to be. They are constrained by the electron neutrality equation. And then the bonded potentials, the distance and force constants for the bond and the angle. For the flexible one, for the rigid one, you get rid of the Ks, right? The Ks are infinite effectively, so you get 5 parameters. So how do you fit that? Typically to match experimental data, or you can try to derive them from higher level of theory like quantum mechanics and fix those parameters, right? So again, we don't really cover that in this talk, but essentially the message I want to get across is that the design of a model is a balance between accuracy and computational expense. That's always present. And also, in terms of the number of parameters, like I said, right, you have to try to use the simplest model possible, but not simpler. Okay, so now on to coarse graining, right? So I told you that depending on the type of model, we can access different length and time scales. So this is a kind of simple schematic I borrowed from a paper. You see the length scale here and the time scale there, and typically the more kind of deeper level of theory models will be here, right? DFT quantum calculations will solve problems for individual molecules or small aggregates of molecules, etc., at a very accurate high level. But then you cannot do, large liquids, right? Simulations. Maybe you can now, but okay. And so you have to simplify. If you want to go here, you have to simplify. So now we go from quantum description to classical description, right? So classical description ignores electrons, etc., and so it takes into account, it assumes that everything is classical. So you can now access longer times and length scales. And then you can keep doing that, and that's what I'm going to talk about next, is this coarse-grained MD, which still retains a discrete representation of reality. So all molecules and atoms, etc., are discrete. But they're much more simplified, so we can access much larger time and length scales. You can keep doing that. My knowledge stops here, right? But we've already heard talks about higher level, like Brownian dynamics, or I missed the word now. Even continuum models, right? So when you abandon or start abandoning the continuous description of the discrete description of reality, you can get hybrid models which mix discrete and continuum, and then all the way to fully continuum models, okay? I'm not going to talk about this. I'm going to stop at the coarse-grained MD level. So there are essentially two ways. Let me go back to the previous slide just to say that there are essentially two ways of doing coarse graining, right? In fact, there are three, as I will explain, but two conceptually different ones. One is bottom-up and the other one is top-down. So bottom-up, the principle is you start from down here with a very high-level description, and you simplify progressively your system. So keeping every time you simplify, you make sure that you describe the correct physics from the higher level theory as you go up the ladder, okay? So that's bottom-up coarse graining. You can also do top-down coarse graining, which is, okay, well, I'm really trying to describe an experimental system. Sure, I can fit my parameters of an atomistic model to the experimental system, but also I can fit the parameters of a coarse-grained model to the experimental system. So we're always trying to match the experiment. That is top-down, okay? And then there's also a hybrid way which combines the two, and that's what essentially we are using. So bottom-up, these are just some examples. Again, I'm not particularly an expert in bottom-up coarse graining. I know a little bit about these approaches, but they have been developed by many different groups. So essentially, you start from a higher level resolution. You can start from quantum mechanics. There's been work done that way, but usually you start from an atomistic description, and then you coarse grain it to a higher level using this, or to a lower level of theory using this approach. So the advantage is it's based on rigorous statistical mechanical theorems, right? So you can derive statistical mechanical equations that show you that there is a unique way of mapping from a higher level to a lower level, right? Depending on your target properties. And depending on the target properties, you have different flavors of this bottom-up coarse graining. So you can do Boltzmann inversion, essentially fitting the structure factors or the RDFs from your atomistic to the coarse-grained. You can do force matching, which is essentially trying to match the forces between the atoms in the coarse grain and the atomistic, or you can minimize the relative entropy between the two different models. Depending on which way you choose, you will get different answers for your coarse grain model, okay? There's a debate about which one of these approaches is best. I'm not going to comment on that. But the main advantage is that once you do that, because it's based on rigorous statistical mechanics, then it has the potential to be predictive, okay? So you don't need experimental data to anchor your system. You are just essentially going up the ladder and making the model simpler, but trying to do predictions of what is going to happen in experiment. The downside, of course, is that precisely because you don't have those anchors, then if you move away from the conditions in which you parameterize your model, it can no longer work, okay? Or it may fail. And I've, in fact, experienced this with, I had a postdoc for a while trying to do inverse Monte Carlo of a surfactant system. And the model we got depended on which data we used to derive the coarse grained, okay? So if we tried to fit a micellar system, we would get a micellar system. We could do predictions in the micellar region, but then it wouldn't predict the liquid crystals at a later, higher concentration, and vice versa, okay? I'll show you some graphs where that is more evident. And so this is just a schematic depiction. You start with an atomistic description, and then you fit, in this case, the RDF. So you would be doing Boltzmann inversion or inverse Monte Carlo. And that coarse grain model is the best fit to that representation. And that gives you then an ability to run larger simulations using this. So top-down is the opposite approach, right? We abandon any knowledge of a higher level model, right? We assume that we don't have it. We just try to develop the simplest representation of the experimental physics that we are seeing. There are essentially two approaches. One you can call generic or toy models, right? This is very widely used by physicists, for example, to try to understand physical phenomena in a very simple and relatable way. They are good to represent general physical principles, but then it's difficult to translate that to specific experimental systems, as you would expect. Or you can use a fit to a subset of experimental properties, and they're what we would call the chemically specific models, but then they lose transferability when you move away from that fit. So essentially, they do not require or imply the existence of a higher resolution model. The downside is that they tend to be less rigorous because they're not based on principles, and they're generally under constraint. So it's non-unique, right? It depends on which way you parameterize, you get completely different approaches. So this is just another example from Athanasios Panagiotopoulos' work. So this is describing, again, a surfactant system, a micelle formation, using this very simple lattice model of surfactants. So you can see how simplified you can get and still represent the basic physics in the system, okay? So this is based on no atomistic description whatsoever. Okay, and this is the approach we are using. We are using a bit of both, okay? So we are based on something called the Martini model, which is originally a top-down approach, but it has become more and more bottom-up as the model has been developed. And our approach for deriving this model is very much hybrid, right? What I mean by hybrid is that you do start with a higher level of theory. We started, in fact, from quantum calculations to determine parameters for an atomistic model, and then use the atomistic model to validate increasingly coarse-grained models. But at every step of the way, we also do a kind of sanity check against experiments, okay? So, for example, I'll show you that in some cases, we use the atomistic model to validate the surfactant description, and then we use the silica model or we use the data on silica to validate the mesoscale model, etc., etc. Okay? So what this means is that what we are trying to do is to develop a more simplified description of the system, but that still captures the basic physics that we are interested in, okay? And that still represents a realistic experimental system. So we can tell experimentalists then that, yes, we are synthesizing silica at this concentration, this pH, this temperature, right? So it's directly mappable to experiment, okay? Okay, so that's the end of kind of the pedagogic part of the talk, right? So this is about modeling and coarse graining, and now I'm going to go into the materials that we are actually trying to synthesize. So this research, as Desho mentioned at the start, is about nanoporous material design. And so what we're trying to do, in the kind of research vision of the group, is to try to establish links between synthesis parameters, so what I informally call the soup, right, where experimentalists mix ingredients and shake them and heat it, and then at the end you get a material, right? That's where my knowledge of the process ends, right? This is, yeah, it's a soup. So you put the material of the soup in and you change the conditions and you get different materials at the end, right? And so what we're trying to do is to establish relationships between the synthesis of conditions and the structure and properties of the material, okay? And then once we know what the material looks like, then we also establish theoretical relationships between the structure and properties and the performance of the material. And that's where the adsorption that Desho mentioned comes in, right? I'm not going to actually talk about this step. This is a different area of research where we try to predict the behavior of material for adsorption, gas separation, etc., based on knowledge of the structure and properties of the solid. What I'm going to talk about today is the first step. Can we relate synthesis conditions to structure and properties, okay? So for that, actually, it is quite challenging to do. And so we need to use very large length and time scales, and so coarse-grained models. So this is the prototypical material we're looking at. We've looked at, as you'll see during the talk, at variations of this kind of material. So they are formed by silica walls. They're typically amorphous. This looks a bit crystalline, but it's not. They're amorphous silica walls, but they are ordered on the mesoscale. So these pores are ordered, in this case, hexagonally, but they can also be ordered lamellary or cubically or etc. Right? So there's mesoscale order, but not atomistic level order. So this kind of order is enforced by interactions between a surfactant template, right? So the surfactant is what forms these kind of micelle arrangements, and they interact with the silica around it, and that's what generates these mesoscale structures, okay? Now, no one really knew how that happened, and so we're trying to generate some models to get some insight into this, and then use it to make predictions about this kind of system. So, of course, the challenge is that there's a lot happening at the same time. So the self-assembly of the surfactant, right, which I'll talk about in a second. There's reactions, chemical reactions, condensation of the silica in the solution as well. There's phase transition, so there's phase separation between dilute and the concentrated phase, etc. There's nucleation of the silica material, etc. Everything is happening at the same time. Of course, we cannot represent everything, but what we need to do in the model is try to retain the key physics and simplify all the rest. So, going through the ladder, right, of how we developed this model. So we started by doing quantum calculations on small silicate molecules. So there was no atomistic model of silica when we started this work. Okay. And the main reason is because experimentally these silica species don't really exist. They're transient, right? So they react very quickly and polymerize and form a gel, and so you can't really measure their properties. So we started with quantum calculations, used that to develop models for, or parameters for, an atomistic model of silicon. This was the first model of silica published, I think, as far as I'm aware. And then we combined that with, of course, water, counterions, and a surfactant. So the typical surfactant for these materials is an ammonium surfactant, which has a positively charged head and a hydrophobic tail, okay? And the length of the tail is also important because it gives rise to different pore sizes. So these surfactants tend to aggregate. They're amphiphilic, right? And for those who don't know what that means, it means that there's a balance between these interactions. So this part of the charged part of the surfactant wants to interact with water. The non-polar part doesn't, and so you give rise to this kind of frustrated, in a way, arrangements of these surfactants. For example, micelles or liquid crystals, etc. So then the next step is, okay, we have the atomistic model, we validated it, etc. And now we need to coarse grain it. So the way we do it is we lump together a set of atoms, right? So for example, these 4 tail atoms turn into a bead, the head atoms turn into another different bead, etc. And then you describe them using a coarse grain model. So these interactions are now very effective, right? So they lump together a lot of the physics in the system, but you can still see that you're still representing your surfactant as something that is amphiphilic, right? You have a polar head and then, you know, an apolar tail, okay? And we developed, again, this new coarse grain model for silica monomers, which can then also polymerize and form oligomers and so on. Okay, so this is an example of a validation step where we look at the pure coarse-grained surfactant water solutions. This is the experimental phase diagram, right? So what happens in these kind of self-assembly systems is when you have a very dilute solution, the surfactant dissolves in the water, so they're just monomers floating around. And then you hit a threshold, which is called the critical micelle concentration, right? At that point, the surfactant, essentially, it's almost like you can think of it as a solubility limit, right? The surfactants are no longer happy on their own. They need to aggregate, right? There's those non-polar domains start to aggregate together and they form micelles, right? So these micelles are reproduced by the computational model. And in fact, as I'll show you in the next slide, they match experimental data for this. As you increase the concentration, you change the curvature of these systems, right? So if you have too many surfactants, the micelles are no longer stable. They merge and they form these elongated worm-like micelles, right? Which we can also reproduce. And then as you keep increasing the concentration, remember this is all without silica, then you can form these hexagonal liquid crystals. So these are now dominated by surfactants, more than 50% weight. You get hexagonal phase here, and you can get a lamellar phase here. And in the middle, you get a bicontinuous cubic phase as well, okay? And our model is able to reproduce all of that for the surfactant. Now, one thing before I move forward is that in the materials I showed you before, that also form hexagonal phases and lamellar phases, etc. Those are all done experimentally in this regime of micellar phase, okay? So it's not the self-assembly is not caused by increasing surfactant concentration, but by adding silica into the system. So keep that in mind as we go along, because I'll show you what the effect of silica is. Before I do that, let me show you the quantitative validation against experimental data. So this is trying to reproduce the aggregation number of the surfactant as a function of concentration of surfactant. And you can see that our simulation points overlap on the experimental trend pretty well, even though this is a very, very simplified model, okay? So this is just an example of this kind of validation. So we can validate against the higher level of theory and against experiment at every step of the way. So this is a validation against a higher level of theory, right? So now we have silica in the system, we simulate a single micelle, and we look at the density profile to see where the silica is and whether that compares well with the atomistic level. And you can see that the coarse grain reproduces the atomistic description in a good way, okay? Okay, so what happens in the system? I'm going to have to move faster, I think. I overestimated the time. So when you add silica to the system, the first thing that happens is you start from a micellar distribution and you get elongation of micelles. So why does this happen? The silica is negatively charged. This synthesis takes place at high pH. So surfactant is always positively charged. The silica is negatively charged, right? That creates a counter-ion effect. So the silica adsorbs very, very closely to the surfactant. It's very strongly adsorbing. And this adsorption at the surfactant interface screens the repulsion between the positively charged head groups. So the head groups repel less, which means that you can decrease the curvature, right? So let me think of it a different way, right? So you have a surfactant, and you have a neighboring surfactant and a repulsive positive interaction at the surface. That means that within that micellar aggregate, the surfactant heads will try to be as far apart as possible, but not further apart, because they're constrained by the volume of the hydrophobic region, okay? So that essentially that balance between the hydrophobic volume and the hydrophilic area per head group dictates the curvature of the aggregate. If you now add a counter-ion to it, right, it diffuses or it screens the repulsion between the head groups, so they can now come closer together, mediated by the counter-ion. So you reduce the area per head group, you decrease the curvature. That allows you to form these elongated micelles, whereas without silica, it would be a spherical aggregate, right? So you're reducing the curvature. So then we showed that actually under experimental conditions, this is a landmark kind of benchmark paper of these materials where they looked at the detailed silica speciation. So we used that experimental information to map it into a coarse grain model, and we showed that under those conditions, exactly the same structures as predicted or as shown experimentally were predicted, namely these hexagonal mesophases. Okay, so this was the first time that any model was able to predict the formation of this kind of structure in the computer. Okay, so as you might be thinking, right? Sorry, I'm just going to go back. So with silica monomers, you only form these elongated micelles, but I haven't explained to you how we go from that to these aggregated hexagonal liquid crystals. And the answer is you let the silica polymerize. So when you add monomers, it goes into worm-like micelles. But if you now let the silica form dimers, which happens in the reaction as you go along, right? The silica polymerizes and starts to aggregate. Then those dimers actually promote intermicelle aggregation, right? Let me show you the next slide. I think I have no, actually I don't. So the way this works is, again, now we have still this screening of the attractions, right, of the repulsions of the head group. So you have lower curvature, but crucially, now we have two negative charges bonded together. So you have a multi-charged counterion. That essentially forms a bridge between adjacent micelles. So one side of the counterion is attracted to one micelle, the other one to the other micelle, and it allows them to aggregate together. Whereas if they didn't have that, they would be repelled. Okay, and so that actually allows you to transition from these worm-like micelles into these hexagonal liquid crystals. And we've shown that this is reversible, so it's equilibrium transition. Okay, so that helps us to explain again how we can go from a micellar system by adding silica through a cooperative process into these hexagonal liquid crystals. So we were able to trace essentially the whole mechanism of this material synthesis from the start until the end of the material formation. So very briefly, we can then play around with this, right, which we cannot do experimentally, but we can do computationally. So we can isolate variables. That's the advantage of doing computations. So we can ask, how does silica condensation affect mesostructure? So we can start with dimers. That gives you hexagonal phase. You can keep the silica concentration constant, but now condense these into tetramers and then to an octamer, right? So everything is kept the same. You just condense the silica. And you see that that actually leads to another change in curvature. So we are concentrating the charge. These are much more charge dense, these octamers, right? So the density of charge allows you to even lower the curvature further and transition to a lamellar phase, okay? So again, we're trying to explain how we transition to these phases based on simple physical understanding of what's going on. We can show the same with the degree of charge. So we can go from, we can keep now the speciation constant, but we protonate or deprotonate. So this would, in a way, represent a change in pH of the solution, right? So as you change that, again, you change the degree of charge. That changes the curvature of the aggregates, and you can go back to hexagonal phase at lower charge, okay? We can also add a co-solvent, right? So essentially, by doing this, we are now filling the volume. So now we're not playing with the repulsive surface of the micelles. We are now playing with the volume of the hydrophobic region, right? So we can fill in that volume by adding something non-polar like benzene, and that goes to lamellar phase. And then if you remove the benzene, it goes back to hexagonal. And that's exactly what experimentalists see by using these co-solvents, okay? And then just we showed that we can actually reproduce the whole family of these periodic mesoporous materials at different conditions that match experiment. So I'm probably running out of time. Do I have 5 minutes, Desha, maybe? Or okay, so I will skip all of this. We've looked at other materials like hybrid organic and inorganic materials. And now, more recently, we've been looking at bio-inspired materials, so trying to emulate biosilicification, which happens in nature, using our models to try to understand how this process goes about and trying to produce more environmentally friendly silica materials. But in the interest of time, I will skip that. And then I just want to tell you a bit about this reactive model. Okay, so this will be the final bit. So all of the simulations that I showed you before, right, pre-assume a given silica condensation rate. Okay, so let me show you. So you can represent this, the experimental progression or the progression of the experimental synthesis on this kind of diagram where you have the self-assembly on the horizontal axis and the silica polymerization or the condensation of the silicates on a vertical axis. Okay, so in experiment, these are more or less happening at the same time. In the simulations, however, we do it in steps. So as I showed you, we start by self-assembling the surfactant without silica. That's the first step of the simulation, the reaction. Then if we want to introduce silica, we add silica to the system, right? So we introduce the monomers into our simulation and run it again. And that leads to the worm-like micelles I showed you before. Now, if we want to simulate the effect of silica condensation on this, what we do is we remove the monomers, we load dimers onto the solution, and we run the simulation again, okay? And that's how we got the hexagonal phase. And this is because, of course, our model is not reactive. It cannot simulate a reaction on the fly. And as I told you, experimentally, that's not the case, right? The reaction, the self-assembly can progress simultaneously. Now, for these materials that I showed you before, the reaction is actually much faster. Sorry, the reaction is much faster than or much slower than the self-assembly, right? So which means that we can self-assemble, assuming no reaction takes place, and then jump to a later stage where the reaction has taken place, self-assemble again, and so on. And that is a good representation of the actual case. Now, with the bio-inspired silica that we were working on recently, that's not the case. The reaction is much, much faster. And so we actually now need a model that can represent the reaction and the self-assembly at the same time, okay? And so we've developed this called reactive coarse grain model. So we are going from the previous work from atomistic to non-reactive coarse graining, and now we're going to reactive coarse grain. So we have to devise a framework that allows us to connect dimers, to connect monomers into oligomers, and then also break them, because this reaction is reversible in practice, okay? So, you know, we have a student working on this, André, for several years, essentially his whole PhD, and he managed to come up with this rather ingenious approach where we add sticky particles. So this is a silica monomer, the gray sphere, and then we add sticky particles at the 4 tetrahedral positions of oxygens where the reaction is likely to take place. And then we counteract that with repulsive virtual sites to prevent non-tetrahedral arrangements from occurring, because they don't occur experimentally, and also to keep the reaction order, the coordination number, in check, right? So we want to have maximum 4 coordination number, not more than that. And so he's adjusted the parameters to match experimental data on the silica condensation rate with over time, and we get, you know, good agreement. And then that allows us to simulate the reaction in real time. And this is just an example following 2 silica monomers during the reaction over time. You can see that they are separated here initially, they fluctuate, their positions, etc. And then when they come into close contact at the right orientation, they form a bond. Okay? And the bond is purely physical, there's nothing chemical about it. It's just a very strong Lennard-Jones interaction, right? And then they essentially diffuse as a dimer, right, during this period. So much less, so the distance is more or less constant. And then at some point, they get a kick from someone else, right, and they break, okay? And they break and they go about and do something else, okay? So they're separated. So this demonstrates that we are able to describe a reversible reaction, and the kinetics are similar to experiment because they match the experimental kinetic data that I showed you before, okay? And so using that, we are now able to simulate self-assembly and reaction at the same time. And this example is an example of micelle encapsulation, as a very simplified process where you form a micelle from solution, and that micelle is coated by a layer of silica. Okay, so we start with a random distribution of monomers and silicates, surfactants and silicates, and then the surfactants start to aggregate, and you can already see at this stage that, well, you can't because it's very small, but you can trust me that you can see aggregates of silica forming already in the solution at this stage, and in fact, in particular, close to the surfactant interface. So then these micelles grow, etc., and then you reach a point where you have protomicelles that are almost completely covered in silica, and I thought, okay, this is going to be the limit. It's not going to progress further than this because they are essentially frozen by the silica shell. But in reality, it's not. And that just shows that the reversibility of the silica reaction is key to this encapsulation process, because what happened was that as the micelles approached, the silica was able to open and accommodate the fusion of the 2 micelles. We followed that in real time, and it was really neat to see. And then eventually you form a single micelle, which is now coated with a nice layer of silica. Okay, and just to show you that that's the case, so this is the kind of structure you can form. This is a hexamer of silica around at surfactant head group, and here you can see if I cut it, this is the layer of silica around the micelle, and you can see that it's kind of hollow, right? So the inside is surfactant. So this would be what would happen if you then burned off the surfactant in calcination afterwards. Okay, you get a silica shell, right? So this is kind of reminiscent of silica nanoparticle synthesis as well experimentally. Okay, so hopefully that's the end of it. So hopefully I was able to teach you something new about modeling, in particular coarse graining, and how basically the main take-home message is every model is a compromise, right? Every model makes assumptions, and you should not take that for granted. You should always think about how you validate the model, how you improve it, etc., and whether it's the right model to answer the questions you're trying to answer, okay? And then apply that to self-assembly and solution, in particular in the synthesis of silica materials, and show you how these different physical variables can change the way the system evolves in time and can change the morphology and the structure of your materials. Okay. So, of course, this work was not done primarily by me. It was done by a lot of very clever people working with me over the years. In particular, the work I've showed here was the first mesoscale model was developed by Germain while I was still in Portugal. The bio-inspired work was then followed on by Alessia and Tom more recently, who just graduated. So thank you to the funders, and thank you all for your attention. Happy to answer any questions.
Thank you very much, Miguel, for this eye-opening talk about self-assembly and, let's call it, intelligent modeling.
Your words, not mine.
The floor is open for questions. Coming.
Thank you. So very impressive work, Miguel. So I was wondering about, so I have a question to the reactive, non-reactive models. So maybe I missed it, but how do you exchange your monomers to dimers in the reactive model?
In the non-reactive model?
Yeah.
Oh, you do it by hand, right? So you take the final configuration of the monomer simulation, right? You remove all the monomers, so you delete them from the trajectory, right? Or from the configuration file. Then you resolvate the aggregates. So you keep the aggregates in place, you resolvate, you first add the dimers into the solution space, then you resolvate, and then you let it run.
So you don't replace them one by one?
No, you don't replace them one by one. You could do that, right? We thought about doing that. You could do that, for example, with a kind of hybrid MD Monte Carlo step, and that's possible to do. But then we try to go to the reactive way instead of doing that. That would probably be a bit more realistic. So the problem, of course, is that you really don't have information about the chemical potential of these species.
Yeah.
So you cannot really develop a robust acceptance trial for removing or replacing a dimer with a monomer, right? Yeah, you can guess, but it's not going to be very realistic.
And in the reactive model, so what is the interaction between the patches? So how do you?
So the sticky particles interact with other sticky particles through a very strong Lennard-Jones potential, because it's still based on the Martini, which is Lennard-Jones based. So they interact very strongly at very short distances. So it has a short cutoff and a very deep well. So when they come into close contact, they will attract, and if they're far apart, they won't. Now, if you just do that, then you will have essentially, you can have up to number 8 or 9 coordination, because you can just fill or surround the central monomer with other monomers. So in order to keep that coordination number at 4, and keep the tetrahedral orientation of the silica, we had to put those virtual patches, which are essentially repulsive. Let me show you the potential map, which I have to skip over. Right. So this is the potential map here. You see that it's a cut, right? So this is the plane of this sticky particle, and you see that in this plane, the only point at which it can react is really in the vicinity of that sticky particle. And once one monomer attracts there, then you don't have any well. The other monomers don't feel the well because they're too far away, right? And they're drowned by this virtual site repulsive interaction here, okay? And of course, if you cut in any other plane with the tetrahedral, you'll see that's also the case.
And you fit, last question, you fit the parameters to match the association, dissociation?
The kinetics,
right?
yeah.
Okay, thanks.
Yeah. So one thing I would add also to this is that this is highly coarse-grained as well. There is no information about reaction kinetics other than fitting to experimental profiles, right? So we don't have any activation barriers. We don't really describe the intermediate species or anything like that. It's just a purely kind of heuristic bond between the two sites.
Canonical scheme would have been my question, but you shut it down.
I mean, I'm not shutting it down. It's certainly possible. We just didn't go that way.
Okay, thank you very much. It was very, very nice talk. And my question is concerning what is important for listening to the youngest one. You remark about the force field matching procedure, and nowadays there is a tremendous article in which published if your potential based on some machine learning based force field using some DFT or CC or high-level ab initio quantum chemistry is practically something which describes the nature. What is your feeling about this?
Yeah, I mean, that's an interesting philosophical discussion that we could probably spend an hour on. Maybe later after the political discussion, we can discuss this. I mean, honestly, I think there's a lot of potential in these machine learning potentials, right? I think the basic philosophy is that you describe the quantum chemistry, you describe, you access longer time and length scales at quantum level accuracy, right? Okay, that's fine. But of course, the model is only as good as the quantum data that you use to fit it. So if the quantum model already has approximations and flaws, those will amplify in the machine learning. If you can do, for example, we were discussing yesterday, coupled cluster machine learning potential, right? I mean, in principle, those will be accurate. But then there's also the question about the breadth, right? So, okay, you can describe water by fitting the pure liquid, but then you put it in the vicinity of a protein, and it doesn't behave like water anymore because those data were not used to fit. That's, I think, my concern. I mean, things are getting better and people are improving, very clever people working on improving these things. So in the future, I think we will see a bigger role for this kind of model. At the moment, I mean, maybe I'm old-fashioned, but I still prefer kind of the physics-based simplification as you go along, and that's been the approach we've used.
All right, any more questions? In that case, I would like to thank Miguel for this great talk.
Thank you.
Okay, České Budějovice is a nice town in South Bohemia, and it's famous for two things. One is Švejk. Who is it who read the Švejk from Jaroslav Hašek? If you didn't do so, please do. So it's great. It's about the absurdity of war, and it's becoming more and more relevant in this age. Okay, the other person about whom České Budějovice is famous is Milan Predota. Our next speaker, who's working at the University of South Bohemia in České Budějovice, and he's gonna talk about molecules in motion, electrokinetic phenomena. So he's gonna talk about everything, which is the basic topic of this conference. Milan, the floor is yours.
Thank you.